Hey guys, here is your introduction video to one of our special right triangles that we're going to learn about. And basically, it starts with a right triangle just like before. The difference is this time I'm going to actually make the triangle isosceles. Okay, so it's kind of a special case, hence the name special right triangle. The good news is, in any right triangle, we still know we have the Pythagorean theorem that we can use, and that's going to come into play here today. So we have an isosceles right triangle, and it'd be nice to know what the measures of these angles are. So can you tell me what the measures of these two angles are if this is an isosceles right triangle? All right, hopefully you realize that they both have to be the same, so therefore they both have to be 45 degrees. Okay, so again, since it's isosceles, we essentially can use the base angles theorem. The sides are congruent, so the angles across from them are congruent. And since that's already 90, there's only 90 left over for the whole triangle, which gets split up evenly, 45, 45. So there's your first special right triangle, fondly referred to as the 45, 45, 90 special right triangle. Okay? And the whole reason we're going to explore this is because we want to be able to find the side lengths, of course. And you're going to see, through a little bit of algebraic magic, we're going to be able to find a pattern to come up with the side lengths of these without actually having to do the Pythagorean theorem. So let's try to get there. Let's do a quick example here where I label this side 6. This side I don't know, I'm going to call x. This side I don't know, I'm going to call y. And the typical question would be, please solve for x and y. Well, it shouldn't take too much to figure out what x is. Since this is isosceles, this leg is 6, means this leg has to be 6 as well. Right? Automatic, done, freebie. Now we got to solve for y. So up until, the end of this video, as far as what we know now, I would hope everybody would set it up like this. 6 squared plus 6 squared equals y squared. And if you want to call that c, that's fine. I get it. But it doesn't really matter what variable you use. Okay? So the leg squared plus the leg squared equals the hypotenuse squared. Let's solve for the hypotenuse the old-fashioned way. This would be 36. 36. That would be 72. And then I need to take the square root of both sides. So if I take the square root of both sides, I get y equals the square root of 72. But of course, I'm going to need to simplify that, not decimal form, just simplest radical form. So let's do that. So this becomes the square root of 36 times the square root of 2. The square root of 36, of course, is 6. And the square root of 2 is just the square root of 2. And we finished our problem. And if this was a warm-up question, you get full credit. However, there's actually a little bit of a pattern going on here that you probably can't see simply because of the value that I picked. So we're going to do the same kind of problem again, but this time I'm not going to use the value 6. I'm going to make another isosceles right triangle, 45 degrees, 45 degrees, but instead of calling this or giving this a value of 6, I'm going to give it a value of x. That makes this one x, and I'll still call this one y. And I still want to solve for y, but I want to solve for it in terms of just x's. So the good news is I still set it up the same way I did before. I still do this. I still do this, but I'm not going to use 6. I'm not going to use 6. I'm going to use x and x. So my setup is going to be x squared plus x squared equals y squared. The leg squared plus the leg squared equals the hypotenuse squared. So I don't have any numbers, but I can still try to simplify this. Excuse me. X squared plus x squared is 2x squared. No, not x to the fourth. We're not multiplying these. We're just adding them together. I have an apple here. I have an apple here. I have 2 apples. And that equals y squared. And at this step, I'm going to do the same thing that I did before also. That's like when we got to here and we said, okay, let's take the square root of both sides. I'm going to take the square root of both sides. Square root, square root. Well, the square root of y squared, of course, is still y, just like before. And the square root of 2x squared, I'm just going to leave for a moment as that. And that's actually, pretty good right there. The problem is that doesn't reveal anything. Like, I don't really understand, or I would understand why you wouldn't understand what the pattern is just by looking at that. But we can clean this up just a little bit. Remember how we broke this down to square root of 36 times square root of 2? Well, I don't have 36, but you know what I do have? I have the square root of x squared and the square root of 2. So I'm going to break these two pieces apart. Square root of 2 times the square root of x squared equals y. Same thing I did here. I know I put the square root of 2 second here, but it doesn't really matter. It's the same pieces of the puzzle. The square root of x squared, of course, is x. This square root of 2 I can't do anything with. And then usually we put the x in front. So I'm just gonna rewrite this. X times the square root of 2 is actually my y value. And this is important. Okay? That's important because if you look back at what we had before, we had the leg of 6, and the hypotenuse was 6 times the square root of 2. In my generic example, I had a leg of x, and a hypotenuse of x times the square root of 2. Can you kind of see the pattern? Or I know you're going to want to see another example, but can you sort of see it? 6 square root of 2, x square root of 2. In fact, it doesn't actually matter what the leg is. No matter what, I could pick any leg you want. If it's an isosceles right triangle, let's pick 10. Okay? If that's 10, I'll call this x, I'll call this y. We should be able to get this pretty easily. Of course, that's 10. And if we follow the pattern, right? The leg times the square root of 2. If I follow the pattern, this becomes 10 times the square root of 2 without even having to do the Pythagorean theorem. So in a special right triangle, the pattern is, here, I'll write it actually down here. If you have a 45, 45, 90 special right triangle and your leg is x, right? The 45-degree angle goes with the x. Well, then the other 45-degree angle also is x, right? They have to be the same. And the 90-degree angle is the leg, which is x, times the square root of 2. This is your pattern. So all you have to know is what one of the legs is, and you can get the entire triangle. For example, what if this leg, not drawn to scale, of course, is 1094? What's this leg? 1094. What's the hypotenuse? 1094 times the square root of 2. Done. You do not need to do 1094 squared plus 1094 squared equals c squared and solve for c and get simplest radical form. If you understand the pattern, this works every time, and it only works because it's an isosceles right triangle. That's the key. Okay, so hopefully that's a good start for you. On Monday, we'll do some practice problems together, but I'm hoping this will at least give you a head start. And if you have any questions on any of this, please be sure and ask. Have a great weekend.